Okay, our next and last speaker of today will be Jeanine Van Order, and she will talk about algebraic cycles on spin-Shimura varieties and special values of L-functions.
Thank you. Thank you. Thank you for the invitation to speak here. It's a huge honor, as always. So I'll give a talk today about something which is actually rather technical. And what I will do instead of diving into the details is give an overview as to why anybody would want to study algebraic cycles. So let me begin with the sort of motivation. So algebraic cycles and heights. So generally, well, in arithmetic geometry, we study algebraic cycles, which are finite Z-linear combinations of closed subvarieties of a given codimension. Let me write that. So Z-linear combinations, closed subvarieties of a given codimension. For two principal reasons. On the one hand, they are the building blocks. The building blocks and also the detectors of arithmetic complexity. So let me make some pointers here. As both as building blocks over the theory, and also as detectors of arithmetic complexity. So I will make more precise what this means. So detectors of arithmetic complexity so building blocks, we use them intersection theory. So you have sorry, I haven't written this well. So you let X be the variety. Yep. And so you have invariance of the variety. You have an ambient variety X, and you consider finite Z-linear combinations of closed subvarieties of a given codimension. Building blocks, you can use these to study invariance of X. You also have some notion of Chow groups, intersection theory, which I won't get into. But on the arithmetic side, arithmetic properties so cycles over number fields detect a lot of, or they carry arithmetic information. Let me just clarify this a bit. So one reason for this is that zero cycles correspond to rational points. So and divisors are really going to be codimension 1 cycles. So these are going to be, n cycles where n is the dimension minus 1. Okay, and so this perspective turns out to be a very useful one. The way we measure the arithmetic complexity is typically using some sort of height function. So let me put this in broad terms. So we very often, so we have various conjectures and theorems in the literature where we measure the arithmetic complexity of a given cycle using some sort of height function. So analytic measure of the complexity. And it typically involves a height function. So I won't. So height function going from, well, okay. If I look at x is the variety and z is the German word, we use the German word Cycle. And typically, we look at some sort of function abstractly on the cycles of a variety taking values in R. So this is very abstract. Let me be a little bit more precise. Can I use this board? Okay. So examples. So two very well-known examples of where we use a notion of a height function or regulator to measure the arithmetic complexity of a cycle are in the conjectures of Birch and Spinor and Dyer and Bloch-Kato. So conjecture of Birch, Spinor, and Dyer, very broadly speaking, okay, Birch, Spinor, and Dyer. I'll put it in sort of general terms here. If you have, let's say you have an abelian variety, A, over a number field. So you have an abelian variety over K, a number field. And you look at its corresponding group of K rational points. You could think of that as being, you could think of it as being the K bar points of A, which happen to be fixed by the natural action of the absolute Galois group of K. And theorem of Mordell and Weil shows that this abelian group is finitely generated. So it will be isomorphic to a certain number of copies of the integers plus a finite torsion subgroup. And it remains a major open problem to characterize the rank. On the other hand, we can consider the corresponding Hasse-Weil L function, which, without talking about L functions, we don't really have a good notion of a Tamagawa number for an abelian variety. It won't converge. So this is sort of you could think of it as being a sort of ersatz Tamagawa number where you introduce a complex variable for convergence reasons. It's some sort of Euler product. You take a product over all primes in the number field, and you have some local Euler factor, which contains information about the number of solutions, or the number of points modulo the prime. And conjecturally, it has an analytic continuation. It's defined for complex numbers of real parts sufficiently large, but conjecturally always has an analytic continuation given by some functional equation where there will be a point of symmetry. So yeah, Hasse-Weil L function. Conjecturally, in many cases we know conjecturally satisfies a functional equation. So if I use the automorphic normalization, taking values at s to 1 minus s, the central point will be at a half. The point is, we have conjecture, which tells us that the rank should be given by the order of vanishing at the center, and moreover, that the leading term in the Taylor series expansion of the analytic continuation around the central point should contain, it should be a non-zero rational number times the regulator, which is a measure of the complexity that I want to clarify. So, yeah. So you've probably seen before the rank prediction. But the other prediction is that the leading, okay, well, let me write it this way. So if you look at the leading term in the Taylor series expansion of the computed L series along, around the central point, what you should have is, I use the squiggly lines here to denote equality up to a non-zero rational number, which I won't describe here, some regulator. So let me use consistent notations here. So this is actually going to be the determinant of some height matrix. Let me just spell out what this is to clarify this relation with heights here. So this is a regulator, which is given by the determinant of something known as the height matrix, where we fix a basis of the k rational points modulo the torsion. And each of these square brackets here denotes, denotes some kind of inner product given in terms of a height. You've got some sort of canonical height, which I'm going to denote by h hat. Okay, so it's regulator. This regulator is a determinant of the height matrix. So roughly speaking, in this situation, the regulator tells you something about the number of points. And the complexity is not only measured in terms of the height, but also in terms of the central, actually, derivative value of the L series. So I won't go, okay, there's some sort of canonical height. The point is, we use heights in this conjecture, and we have theorems when the rank is, when you have, when the abelian variety is an elliptic curve, and you take the number field to be the rational number field, and the rank is 0 or 1, we do have theorems which verify this by various people. And one very striking theorem, which I describe in a higher dimensional context, is that of Gross and Zagier, which allows us to express, in some sense, the central derivative value of the Hasse L series in terms of the height pairing. So the matrix there is just the height pairing. There's rank 1 height pairing of some Hegner point. There is a more general form of this conjecture due to Bloch and Kato. I don't know if I really should spend much time presenting it, but there's a sort of there's also the more general Bloch-Kato main conjecture. And rather than write it down, I mean, there you start with a motive. Motive is really just a collection of information that you might use to is to define an L function. It has various realizations, p-adic, étal, ready. I'm not going to get into this, but you fix a mode of M, you fix an integer n, and you consider its twist, the twist of the motive by n. And you can define some sort of block-Kado Selmer group using Galois cohomology. So yeah, I mean, like the K Galois cohomology of Mn, where Mn is some sort of Tate twist, nth Tate twist of M. And the Selmer group is defined in the usual way. There's some sort of kernel of a localization map, so it's really determined by local conditions. And the group is finite dimensional. Corresponding to the motive, there will be an L series. And the block-Kado main conjecture predicts that the order of vanishing at s equals n of the motivic L function, the twisted motivic L function, will be the same as the dimension of the block-Kado Selmer group. So there's a vast generalization, actually, of the conjecture of Burton, Spinor, and Dyer, and so a lot of the recent progress using automorphic representations and their corresponding Galois representations is, in fact, very often made for the block-Kado main conjecture. So I don't want to go into this, but I will say that there is also a corresponding sort of refined conjecture which will express the Rth central derivative value of the motivic L function in terms of some higher regulator. Yeah. So there's a vast generalization of this conjecture. What I'd like to say something about next, which is sort of related to these examples that I mentioned obliquely, are the kinds of varieties that we actually study to prove results. And the varieties that we look at are Shimura varieties. And you might wonder why would you look at those and what are they? Shimura varieties, broadly speaking, are generalizations of the modular curve. So higher dimensional analogs of the modular curve x naught of n. So upper half plane, modular gamma naught of n, adjoint cusps. So historically, sure. Yep. If you give me time to finish the lecture, I'm going to give a very precise example of a height function, which is some sort of I would like to not define the canonical height, if you don't mind, which is what this is. And what I will do later in the lecture is introduce, in very rough terms, some sort of Arakelov height, which is like it's some sort of function that collects information about the complexity at each place. And there's going to be an infinite component, and then there's going to be a component for each prime p. And the infinite component will be some sort of Green's function, which in the situation I will describe has a very explicit definition, which means that you can hopefully compute the height by evaluating this Green's function along a particular along a particular zero cycle in the theorems that I mentioned, but then in work in progress, certain restrictions or variations of that can potentially be used to compute heights, Archimedean heights, along other cycles. Thank you for the question, though. Yeah? So higher dimensional analogs of gamma naught of n. Okay, motivated by, are there questions? Okay, so motivated by Kroneker's Jugendraum. So theory of complex multiplication allows us to construct generators of all of the abelian extensions of imaginary quadratic fields as special values of certain modular functions. And it's one of the crowning jewels of 19th century mathematics. Hilbert's in his 1900 ICM lecture introduced it as one of his problems, actually, to generalize Kroneker's Jugendraum with a theory of complex multiplication which again gives generators for abelian extensions of imaginary quadratic fields and special values of certain modular functions. He proposed actually to generalize that and consider functions, modular functions of several variables. And then, evaluate these modular functions of several variables, get more algebraic numbers. This ultimately led to the Langlands program as we know it today. So mentioning this problem inspired his students, Hilbert and Blumenthal, to study what are now known as, Hecke and Blumenthal, to study what are now known as Hecke-Blumenthal varieties. Carl Ludwig Siegel also contributed greatly to this theory with the same motivation. I will say a little bit about this example. In the 1960s, Taniyama and Shimura, independently Andre Weil, generalized the theory of complex multiplication to abelian varieties of CM type. And so there's this important work sort of discovered simultaneously by Taniyama, Shimura, and Weil, so there's abelian varieties of CM type. And maybe I shouldn't write it down, but the theory as we know it today, which is highly technical, really comes from Deligne. So Deligne absorbed these works of Taniyama and Shimura and Weil and generalized them. And so he showed the existence of a general canonical model. And maybe I should write Deligne's name here, but then I should also write Langlands, because one of the reasons for so much major interest in these varieties, which are simply generalizations of the modular curve, is that they are an excellent testing grounds for Langlands conjecture, which broadly speaking is a conjecture that any motivic L function ought to come from an automorphic form. And so these are perfect, because these Shimura varieties, they are on the one hand the spaces on which automorphic forms live, automorphic forms with good arithmetic properties. But at the same time, all you do is take the étale cohomology of one of these Shimura varieties, essentially, and you get a Galois representation. So you have a really good environment to test these conjectures. And so Langlands took a lot of interest in this. And so the theory has really developed a lot in the past 40 years, 50 years, 60 years. So the first example, I don't know how much time I should give to this, but the first... Great. Okay, let me go quickly then. So examples, because this is a lot of philosophizing. So maybe I go quickly on this point, but the first generalizations of the modular curve. So first example is really Siegel modular varieties. Okay, so these in some sense are the right generalization of a modular curve. So if you have, you fix an integer g greater than or equal to 1, and you write hg should know the Siegel upper half space. So this is really just going to be the space of matrices. Let me just, so symmetric G by G matrices with entries in C that are positive definite in a sense. And you can view it, if you restrict the, I maybe don't write down the rule, but you can really view it as being an open set of, okay, so Siegel upper half space, degree D, and the group of symmetric matrices, whose definition I won't write down. Okay, so symplectic group, which preserves some alternating form. Okay, so it fixes the alternating form. So it turns out that, this group acts simply transitively on the Z equal upper half space by the natural action. So you have a matrix. So these are matrices in GR, acting on one of these matrices by the and the point is that if you write K to denote the stabilizer of this action, the stabilizer under this action of I times the G by G identity matrix, then this group has a name. It's going to be the matrices Z equals A plus IB with the property that the conjugate transpose times the matrix is equal to the identity. And the point is that there's a natural description of so because the action is, you have a simply transitive action of this group, you can realize this equal upper half space as a quotient. And taking G equals 1. Okay, well, the first thing that you can actually check is that this is isomorphic to the Poincare upper half plane. And in this case, you have identifications. Yep. Okay, and so the orthogonal group is going to be this U1 that I wrote down. And there's a completely analogous description of the Poincare upper half plane as such a quotient. In general, each matrix in the Z equal upper half space gives rise to a lattice. And so let's call that lattice LZ. LZ is going to be it's going to be the obvious thing. You're going to have Z to the G. Z to the G times Z plus Z to the G is going to be a lattice in C to the G. And you get from this a complex, a priori you get a complex torus. Okay, so you get a complex torus, but actually it is a structure of an abelian variety. It comes with a polarization. And and although I won't discuss a polarized abelian variety, although I won't discuss the rich theory that goes into this, the corresponding quotients of the Z equal upper half plane by any congruent subgroup of SB2GZ, in fact, it's not only a Shimura, it's not only a complex variety. Well, maybe I should just write this down, so that there's a lot more structure. I'm just giving a sketch here. So if you have any congruent subgroup of SB2GZ, say, then actually this. So two things I want to say. So the variety that you get. So this quotient of the upper half space by gamma, a congruent subgroup, will in fact determine a complex manifold. Complex manifold of dimension G times G plus 1 over 2. And actually, it has a description as a moduli space of abelian varieties of this type, with a particular, well, in this case, a principal polarization, but you can consider more exotic types of paramodular subgroups and different polarizations. But basically, it'll be a moduli space of abelian varieties with particular extra properties associated to them. And so this is a very rich example, which I won't get into until the very end of the talk. The reason I bring it up is because it is, in some sense, the most natural generalization of the modular curve. A less obvious generalization of the modular curve is coming from a Shimura variety of orthogonal type. So I say very quickly what that is, very quickly then what the height is, and what some of the known results are, and then some of the new contributions, even if I only say them very quickly. So that was one example. Another example will be spin Shimura varieties. These also generalize the modular curve. So here, we start with a rational quadratic space of signature, rational quadratic space. Of signature n2. So n here is going to be any, actually you can take any, n greater than or equal to 0, any integer. So what this means is that V is a vector space of dimension n plus 2, and you've got a quadratic form with the corresponding inner product of signature n2. Okay, so it's some information that you use to, And the geometry here, which can be described in several ways, the generalization of the upper half plane that we need to define a Shimura datum and a Shimura variety is coming from, one way to describe it is through the Grassmannian of oriented negative definite hyperplanes. So you could take just the space of little z here is a hyperplane. So it's going to be, it's going to be a subspace of dimension 2 of the, R, V tensor R, and is oriented. So I'm not going to oriented in some sense, and you have the condition that if you restrict the quadratic form to Z, that it has to be negative definite, say, and this actually has the structure of a. Well, this will give the corresponding quotient space a complex structure. There are several equivalent ways to see the complex structure on here, so that you actually get a Hermitian symmetric domain, but I won't go into detail. There is also, like, by analogy with this case here, there's going to be an action, there's going to be a natural action in the corresponding orthogonal group on this Grassmannian, which also turns out to be simply transitive. There's also going to be, there's also going to be some sort of stabilizer for this action of some fixed base point, let's call it Z naught, of the Grassmannian, and there's going to be a completely analogous way to realize, this Grassmannian as a quotient of this group by this stabilizer. And so in this situation, there are actually two types of Shimura varieties we can look at, one for the orthogonal group, but the one that turns out to be more fruitful for arithmetic applications is a certain extension of the orthogonal group. Okay. And that's the corresponding generalized spin group. So it's defined in terms of Clifford algebras, intersection of the even Clifford algebra V with the Clifford group. But really, you could think of it as being an extension. You could really think of it as being an extension, a non-obvious extension of the special orthogonal group. So you fix a lattice. So I'm going to describe the Shimura varieties now. They're also going to be realized as quotients in this way, but I'm going to do a slightly roundabout thing. Well, they're going to be quotients of, in a very natural sense, by analogy, with the case of Siegel modular varieties, they will be quotients of the domain by arithmetic subgroups. But here I'd be a little bit more general. If I have a lattice in V, I can associate to it some sort of compact open subgroup of the finite adelic points of the spin group under some sort of natural conjugation action of it'll occur as a stabilizer. I mean, there's going to be a very natural way to associate to new lattice this compact open subgroup. So there's going to be some sort of action by conjugation of this group on the idealization of the lattice, and this will be the stabilizer. And the point is, we get varieties in this situation too, and they appear first as quotients of the following type. So first as a okay, so these double quotient spaces, which, I mean, really, if you fix a set of representatives for the finite set, given by this quotient, you're going to get some arithmetic subgroups, which are going to be defined in the natural way as intersections. So let me just write G for the intersection with the rational points with the conjugation. And the point is we end up with, I mean, these are really the varieties we're looking at. So we have some domain, and we've got some arithmetic subgroup. And we've actually got some sort of finite number of connected components of these. And these also generalize the modular curve. So I say very quickly what that is, and then I tell you why it is that people like to look at these particular Shimura varieties is because they have a lot of cycles on them. It's extremely easy to find algebraic cycles on them. Basically, any subspace of signature n prime 2, where n prime is less than n, will give rise to an n prime cycle, or yeah. And so are there questions? Are there questions? Okay, so this also generalizes the case of the non-compactified modular curve. If we take the space of signature 1, 2, given by two by two matrices with entries in Q and trace 0, quadratic form given by n times the determinant. And so this will determine a space of signature 1, 2, and we take the lattice to be something specific. Like you're going to take you're going to be looking at you're going to be looking at trace 0 matrices with minus a over n and c. Okay, and this, if you do this, I mean, if you look at this particular example, you can recover the non-compactified modular curve. This is not obvious, but it's another generalization of the modular curve. So algebraic cycles, I say very quickly. Algebraic cycles exist in abundance here. Like I said, any subspace and signature n prime 2 gives rise to an n prime cycle. So we have, for instance, maybe just write it down this way. By the same construction. That is, you take V prime, you consider its corresponding Grassmannian, its corresponding spin-Shimura variety the same way, and you get a closed subvariety defined over Q. of dimension n prime. And so what this means is we have a lot of cycles that we can work with here. So for instance, a zero cycles will just be rational quadratic subspaces of signature 0, 2. These are always associated to imaginary quadratic fields. So you've got zero cycles. Correspond to spaces of signature 0, 2. And similarly, divisors. Divisors will, well, okay. By what I told you, you'll always be able to get a divisor from considering a subspace of signature n minus 1, 2. But sort of a natural way to construct those is to fix vectors x in the vector space of I guess, positive norms, and then to consider the orthogonal complements and then to use those as the spaces. And so, for instance, you can consider divisors of the following type. I'm not sure if it's wise to write them so explicitly, but OK. Let me just keep what I said verbally, and not because if I write down all the notation, it takes a lot of time. But it is really as simple as what I've described. You know, there's a huge multitude of cycles that we can work with, and when we look at divisors, it's sort of easier because we can construct the spaces as orthogonal complements of particular points, and then be very specific about the divisors. And why do we look at the setup? Well, in the setup, we can look at heights or construct heights. And actually using automorphic forms. So this is a little bit, this is something I will do very quickly. So the divisors, yeah. Special divisors. Are what they called here. So these divisors and these algebraic cycles were studied in a very systematic way by Kudla, who developed a program for getting higher analogs of the Gauss-Sagier formula, where I'm going to explain some progress right now. So in this situation, I want to describe very briefly that we can compute the heights of certain divisors. And we can do that by constructions coming from automorphic forms. So in this situation, we retain the setup from above. You can see the Weil representation. So it's a representation from the two-fold metaplectic cover of SL2 to some space of functions on the finite abelian discriminant group of the lattice. So LV here is just the dual lattice. And you have a corresponding Siegel theta series. So yeah, let me just, so you have okay, so the G I could just forget about here. You have some sort of so this is actually a classical construction, but it was generalized pretty vastly by André Weil. And you also have some sort of space of non-holomorphic vector-valued modular forms on the upper half plane. Very roughly speaking, this space denotes the space of twice differentiable functions on the upper half plane, which satisfy a transformation property with respect to the weight L equals 1 minus n over 2 and representation omega L Peterson's slash operator, and they're harmonic in the sense that they are annihilated by the corresponding hyperbolic Laplacian of this weight. So this is harmonic weak mass forms of weight 1 minus n over 2, and representation. Okay, and so each one of these will have a holomorphic part and a non-holomorphic part, and the holomorphic part will be something that has a Fourier series expansion, a nice Fourier series expansion. It's going to be like it's going to be I'm writing this down for a reason. Okay, so this is okay, so this is just the usual additive character, x 2 pi I tau, and this is the characteristic function for the coset mu in the finite abelian discriminant group. So this is the holomorphic or principal part, and actually the reason I define it is because we know how to construct Green's functions, or by important theorems, due to Borchert and more generally Brunier. We have a way of constructing basically the Archimedean height function, if I can be very brief about it. So let me just write down several results. So there's going to be some sort of, okay, these are generally not holomorphic, but they're going to have a subspace of weakly holomorphic forms, which are forms that basically have Fourier series expansion of this type. They're weakly holomorphic. And there's a short exact sequence. So these are going to be, so for any half integer weight, you're going to have, okay, so you have this space of harmonic weak mass forms. You have some sort of anti-linear weight-lowering differential operator, which goes into the space of holomorphic cusp forms of weight 2 minus L. And the point is that you can characterize, yeah, so this is a certain differential operator, which can be written down explicitly. And so theorems of Borchert and Brunier. So if you start with one of these weakly holomorphic forms with this principal part, and you have one of these equal theta series, the lattice that I wrote down, then the function given on Z, Z an element of the Grassmannian, and G a finite adelic point of the group by some sort of regularized theta integral. So this, let me just write it down quickly. There's a natural pairing on vector value forms. You can just ignore it if you assume the lattice is split. Okay, and really, if I write d mu tau for the Poincare measure on the upper half plane, it's just going to be the constant term in the Laurent series expansion of the limit over truncated fundamental domains for the action of SL2Z on the upper half plane of the same thing. V to the minus S d mu tau. Okay, and the point is, the point of writing this definition down is that this is, okay. So then the function defined by this regularized integral, from this harmonic weak mass form from this theta series, is an automorphic Green's function. Let me just, for a particular divisor constructed from the Fourier coefficients of the principal part of F. So let's just write that down quickly. Is it, yeah. So an automorphic Green's function in the sense of Erich-Kaloff theory. For the divisor. Okay. So there's some divisor that we can construct from the Fourier coefficients of the principal part of the harmonic weak mass form. So we have a finite number of these coefficients to consider. So this is a finite sum, and this is also going to be a finite sum. And then we've got some divisors, which I didn't tell you about, but basically what you can do is, I mentioned before that you can construct a divisor from a rational quadratic space of signature n minus 1, 2. And such a space can be obtained as the orthogonal complement of a point. What you do here is you fix some point in a coset, in this coset of whose such that the quadratic form evaluate at x equals m, and then you use that point to create the complement, and then you literally just get this as the divisor. And so you have a finite, and you assume that these, you crucially assume that these Fourier coefficients, of which there are finitely many, are integers. And so this is an algebraic cycle. And so what does it mean to be a Green's function, an automorphic Green's function? Well, it means that you have a function on the Shimura variety with a logarithmic singularity along this divisor. It satisfies some Green's current equation, which I won't get into. And it's also going to be an eigenvector for some corresponding generalized Laplacian on defining the Grassmannian variable. And the reason, okay, this is a divisor. Yeah. And what this means is that we get what is known as an arithmetic divisor, typically denoted in the literature with a hat, because that means you have two pieces of information here. We have the divisor, which is a finite Z linear combination of codimension 1 cycles on the variety, and then we have this, this Green's function. And the point is, the height in this situation is going to be some sort of function which contains an infinite part and a finite part. And the infinite part, which should give us the special value of the L function, is going to be computed by this Green's function. And so we do literally have theorems where we can prove something to this effect. So let me just say that we have the following important theorem in the Kudla program due to the works of various people, particularly Kudla and his student Schoeffer, together with Brunier-Yang, together with more recent work of Andriada, Gorin, Howard, and Matapuzzi-Pera, which computes the height starting with the Archimedean local height, which is the value of this Green's function along some zero cycle. And I just say very quickly, yeah, okay, it's a theorem due to many people. I just put the initials of all the people I said here. So you have Kudla, his student Schoeffer, you have Brunier-Yang, you have Andriada, Gorin, Howard, Matapuzzi-Pera. Okay, and basically, wow, okay. One, with all the same conventions as before, you have one of these harmonic weak mass forms, and you take a space of signature 0, 2, and you consider the corresponding lattice. And you evaluate this function along the zero cycle. So you're just going to, it's literally a, literally this. And what they show, actually, is that this is, well, okay, so this is going to be some compact open subgroup determined by the sublattice. And you're going to have, I won't get into too much detail, but you'll have the constant term in the Fourier series expansion of the principal part against the Z equal theta series corresponding to the complements of the lattice. And then there's going to be some Eisenstein series corresponding to the lattice that you average over. Implicitly, it's going to have a derivative, and you're going to consider its holomorphic part. And there's this constant term, which is basically going to correspond to the non-Archimedean local height. And then you've got the central derivative of some L function. Okay, so I won't. So here, you take the image under this antilinear differential operator of the form you started with, and then you've got the theta series of the complementary lattice. Okay, and although this looks very technical, the point is that this actually computes the height. So let me write down that, and then say a few words about sort of the direction of research these days. So if you assume that the Clifford algebra of the lattice is the maximal order in the ring of integers of k the imaginary quadratic field determined by the signature 0-2 space, and you assume that the discriminant is odd. So assume that the discriminant of this imaginary quadratic field determines by the subspace is odd, then actually this computes. So I'm going to write this notation here for, okay, so we have, I mentioned before that there's some sort of arithmetic height, there's some sort of arithmetic divisor corresponding to the choice of form. And then you've got this, this zero cycle. And so I'm going to write these square brackets to denote the Arrow-K-law of height. And this is formally, you can think of it as having an Archimedean component. So it has a component of infinity, which is essentially just the value of this function along the zero cycle, plus a finite part, which I won't get into at all. But really, you use integral models of the Shimura curve, and you compute local intersection pairings for each prime. So there's a finite part, and there's an infinite part. And so the infinite part is computed in the work of Brunier-Young, and the finite part is computed in this work of Andreatta, Goran, Howard, Matepus-Lupera, who really work with the integral models of the Shimura varieties, and they do these local to P calculations. And really, what you end up with is a statement of the following types: the degree -1 times the degree of the zero cycle, so the natural notion of degree divided by 2 times the Fourier coefficient at 0 of the principal part of f. So this vanishes if f is hospital, and also the constant term in the Fourier series expansion of this derivative the principal part of this derivative Eisenstein series, plus the same L value that appeared on the other side. So you've got, sorry. Okay, so the same, let me just write it L prime 0. So it's the same L value. And the point is, this ends up being the height function. It measures the complexity of this arithmetic divisor when you evaluate along this zero cycle. And actually, you get an explicit formula here in terms of, this is basically the finite part, this is basically the Archimedean part, and the Archimedean part computes the central derivative value of some L function. So this is one place where we do sort of realize, where the vision or the idea is realized. And so this represents, in many ways, the state of the art for what is known about arithmetic divisors these days. I have about 1 minute left. I don't know if I can go 1 minute over, but in a nutshell. So the next frontier is doing these sorts of calculations for higher codimensional cycles. So the easiest situation you could consider would be the situation with n equals 3. So you take a rational quadratic space of signature 3-2. But it turns out that there's an accidental isomorphism coming from the spin representation of the general spin group of that space of signature 3-2 and GSB4, which means that actually the spin Shimura varieties in that setting are isomorphic to GSB4 Shimura varieties, which are Z equal modulo. Yeah, they're Z equal 3-folds. And so in this situation, I mean, I could write something down on the board, but the generalization of this sort of statement is not known. It goes by various names, one of them being the arithmetic Rallis inner product formula. There are some interesting results in the literature. There is remarkably in that situation work by Kudla and Rappaport, which appears, I think, in the Annales Scientifiques de l'École Normale Supérieure, 2000, where these sorts of local intersections are computed in terms of derivatives of Eisenstein series. And there is recent work by Naomi Sweeting, which appeared on the archive this year, proving some sort of block-Kato main conjecture for certain GSP4 representations with Jacquet-Langlands transfers to the spin group. And she obtains results for rank 0 and rank 1, but she does not use or get a formula of this type. And so what we find, I could speak a bit more and write something on the board. It's work in progress, but if you take the same sort of setup, and there it's not even obvious how to define the heights, you need to find a Green's currents. But what we find actually is that some sort of restriction of the Green's function, which is the sort of analytic manifestation of passing to a divisor, or passing to an incoherent divisor, allows us to compute exactly the L value we expect. And so it seems to be the case that passing to an incoherent divisor might be a useful tool for extending this type of result to higher codimensional algebraic cycles. So sorry for the 3-minute overtime, but yeah.